So Mitra Ebrahimpoor is so I've known her since I think maybe 1.5 years or 2 years. We met at a multiple testing conference, and she talked about basically, I mean, an earlier version of this work, which I thought was really interesting. So it's a work with her advisor Yael Ruman on. So I should say that she's a PhD student in Leiden University Medical Center, and that's yeah, it's a work which stems more from the multiple testing community, I would say. So Mitra.
Yeah, thank you for the nice introduction, Pierre, and thank you in general for all the organization. Because of my busy schedule, you had to email me 1,000,000 times, so it's very nice to be here. Hello to everyone. I wanted to talk about volcano plots and why not to use them, basically. To set the scene, I'm gonna go through the problem that volcano plots are used for. So generally, volcano plots come after the differential expression analysis, where you have a long list of features and you have a few samples. So this is almost always true, even with all the new technologies and fast RNA sequencing and everything, that you generally have, like in my example, 25 samples, and then there are 1,000 features that you have. And then you have to make a decision about these features, these 1,000 features at the end, to see if they're associated with a certain phenotype or not. So the goal is detecting differential expression, and generally it is two conditions. Of course, you can always generalize to more complicated settings, but to keep it simple, I'm gonna assume that we have two groups of, let's say, controls and treatment, and we want to compare and see if there is a certain differential expression of the certain genes present. So the pipeline goes like this. You would pre-process your data, so the usual normalization or scaling of the data. And then you would test each of the features. So you have the total samples, which is, as I said, pretty small and a large number of features. But because you're doing feature by feature, this is not a big problem so far. What you would do is to use a simple t-test. You would estimate the beta, and you are basically testing if this beta from the regression model is 0 or not. That is the whole question. If it is 0, so it has nothing to do with this grouping which goes into X. And if it is not 0, it means that there is something interesting going on there. And then because you have tested so many tests, you have tested so many null hypotheses, M of those, then you would do the BH adjusted adjustments and then correct the p-values for this adjustment. Then, of course, there will be a lot of significantly DEGs, differentially expressed genes, and then you have to basically summarize that big list of discoveries. They're so differentially expressed and discoveries. I'm gonna use them interchangeably. They mean the same thing in this genomics setting. And then, so to make it simpler to interpret the results, you would be like, okay, let's just talk about the top discoveries. And that's when the volcano plots kick in, basically. So how we would talk about the how we would select those top discoveries among all those features is that we would plot all the fold change, so basically the beta hat that we had from the previous slide, and the log 10 of the p-value, minus log 10 of the p-value. Then the idea is that you have the statistical significance here and you have the biological significance here, so you are taking everything into account. And to make sure that you are making a good choice, you would first filter based on the p-value, so those that are significant after BH adjustment, and then you would do another filter of choosing the most interesting genes. So these will be the top genes, basically, those that are both significant and hold a generally large beta hat. And everything will be based on these. So you can easily, even now, just Google any gene expression and volcano plot, and it is a very natural thing to do in genomics. So why not to do this? Why this is a problem? It looks like a logical explanation of selecting your features based on both statistical and biological importance. But the issue is you are filtering your genes twice. You are first filtering by p-value and then filtering by fold change. But what you should remember is that pH adjustment is over all genes. So pH has no guarantee that you are to control FDR over subsets of those genes. So once you apply pH on a big set of M genes, pH is controlled, so the FDR is controlled for those M genes specifically. And if you do a subsetting, there is no guarantee that it still holds there. So you can have a subset that has the FDR of larger than 5%. And then what makes it even worse is that you are, when you are selecting the top genes, you are selecting them based on beta hat and not the t-statistics. And you're basically just ignoring this variation that is going down there, and you're just looking at the averages, basically the difference in averages, which means that because in general, we all know that this variability in measurement just shows that how unstable this information is. And so you are going to choose the large variances. And if by choosing large betas, and then if the non-DE features have large variances, this will end up you just selecting false positives, basically, not the true positives that you're looking for. So if I'm not sure if the audience is very familiar with the moderated t-test, but there is this certain version of the t-test that is used in VOOM package, and it actually makes the story even worse. You can go ahead and read the section on this in the paper. I'm not going to bore you with the details of mathematically what happens, but just know that that's not a solution that actually makes the things worse. So let's see what I mean by making the things worse and what I mean by a problem. So this is the same plot that we just saw. This time I have made the size of the dots with respect to their variances. So a larger dot means larger variance. It is just very clear that most larger variances are here, but there are still many large variances laying over here. And if you select by larger variance, you would just be likely to select these two as the positives. So let's see some notations just to bore you a little bit to see how it actually goes wrong and how bad the problem can get in the real setting. So let's say that we have T as the number of truly DE genes. We will generate some variances and then start to sample from these variances. So because this is a simulation setting, I can, of course, force the data in a way that those with larger variance are truly DE or those with smaller variance are truly DE. I control this with a parameter lambda. So from now on, if you see lambda larger than 0, it means that the truly DE features have large variances. And if it is less than 0, it means that truly DE genes have smaller variances. And when it's 0, it means that there is no correlation between the variance and the true positives. And then I would generate the data simply based on a regression model. I'm still using that simple model of comparing two groups. And then the natural DRL of the p-values adjustment, and then selecting what with the volcano plot scenario. So this is how the results look like. Of course, I have to, I had the t value, I have the sample size, I have the lambda value. So there are many things differing here, but what you see here is basically how often the topmost gene, so the gene with the largest beta is actually a false positive. So this is the rate, so it is well above 40%. And then if you selected 2, how often those are false positives. And of course, if you select everything, you are going towards the BH assumption that it is controlled over M and it goes down. But if you keep your focus on the top genes, then you are actually selecting mostly false positives. And then this is one example of those. They're averaged over several simulations. But this is one example of such case. So I have simulated the data just like what I said before. And this is a volcano plot, but now this here I know the truth. So these triangles here are actually those that are a false positive, but they are clearly well selected with volcano plot. And if you ask your biologists if this is an interesting gene, they would be like, yeah, it has a very large effect size, but it also has a large variance, and there is a good chance that it is a false positive. So of course, many would say that, yeah, this is because of the correlation between the genes and their variances, the whole idea of having larger variance for the non-DEs. But then if you just remove this correlation and use a lambda of 0 in my setting, you still have an inflated type 1 error for your top genes. So this problem won't go away if we assume that there is no correlation between the variance and the nullness of a gene, but then there is no way to check this. So you would never know that you are in a lambda 0 case or lambda -1 case, or even worse. And you just have to accept that your data may be in one of these two scenarios, but there is a good chance that it will still be an inflated type 1 error by selecting with volcano plot procedure. And another example of the same scenario where there is no correlation. So of course, because there is no correlation, you don't see very large ones appear, but you still have lots of these triangles that are selected by volcano plot, but actually are a false discovery. So why this happens? We know. Now let's see what we can do about this. So there are two available methods for alternatives for this procedure that I'm going to go through with. One of them is, of course, BH controls the false discovery rate, so we can still use a different version of BH. And there is also this idea of estimating FTP with its median, or using the FTP bound, which I'm going to go into the details shortly. And then another version of BH that we can use is this FDR with filter. So we call it FBH, or focused BH, as it is in the paper. You may go to the details, but I will give you an idea of how it works. It is a variant of BH. So this one is mostly family-wise error rate, and this one would be an FDR method. So let's go see how median FTP works. So median FTP is a close testing procedure. I'm not very sure that everyone here is familiar with the close testing procedure, but you don't really need to be familiar with the method to understand how it goes. It is based on Symes local test, and it is FWER correction, as I just mentioned. What it does, it's basically allows you to calculate FTP, or its bound, or its median. So basically estimate the false discovery proportion for any subset of your data. So this is a post hoc procedure, so you don't have to assume a certain subset before the analysis or anything. So the method gives you the possibility to do this post hoc, and it is for every possible subset of the data that you can generate. So this is the definition of FTP, and what it does, basically, this whole close testing with Symes local test, it provides you simultaneous bounds, lower bounds for the FTP. So these lower bounds are simultaneous over possible sets. So you are always sure that you have a good estimate for the lower bound of your false discovery proportions over every possibility. So this is already a little bit light that we can use this idea to do the volcano plots, similar to volcano plots idea. So this is how I would write the volcano plots one. So this D is the set of discoveries that are selected based on a p-value less than alpha, and the beta hat based larger than t. So this is the VP selection. What close testing would do is that it will give you the median of the FTP, median estimate for the FTP, or a bound for your FTP. And these bounds are simultaneous over every possible set. So you don't have to worry that if you are going to use a different T and different alpha every time. And you can redefine this set of D. What about the focused BH? The focused BH is a version of BH that controls FDR. It allows you to subset and still be controlling the FDR, but then you need to specify this a priori. But of course, it can be still data dependent. But this already is a red flag here that you have to decide before what your filter would be, and you cannot change it because then you will again have the similar issue. But still, it gives you the possibility to define this based on your data. So if you are very sure that you are interested in a certain subset of the data, you can always use this method. And how it goes is similar to FDR procedure, but it actually controls it over the subset of interest. So this F is subset of interest, and you would use the maximum R in a way that the FDR is controlled over the subset. If you want to know the details, you can always refer to the publication. So now let's see how they are connected actually. So as it turns out, they're very similar. So if you do control the focused BH and create the set D, based on focused BH, control FDR and get the subset D, and then for this subset D, calculate the FDP, it is less than 2 times alpha, and this is actually a bound, so it can be closer to alpha, which is what BH guarantees. So you are actually just giving a little bit in turn for full flexibility of making choices of the subsets. Then if you want to compare them analytically with the simulations, it is not as straightforward because there are like 2 very different approaches. VP selects them based on 2 thresholds. That is the natural volcano plots. Then for a certain alpha, P threshold is given if you want BH. And then for median FDP, you can just calculate this for any subset of your data. So to make it comparable across different methods, what we did to do what one of the methods does and calculate the other method's estimate. So one of them is this one. So what we did was to fix the threshold for beta, and then also for the p-values. This is what volcano plots naturally do. You have a fixed p-value threshold and beta threshold. And then what we did was to estimate the FTP based on different methods. Here you see different settings for lambda. So if there is a correlation between the variance of your genes and their nullness. And then this setting is the one that there is no correlation between the methods. And this is a setting that is actually in favor of the volcano plot method. And already we know that the variances for the null genes are quite small and they won't be selected. And then and this is a setting where you have 24 samples. So the sample size is quite large for these studies, and it won't go away if you have actually a bit bigger sample size. So you see that as expected, of course, the bound, the FTP bound is always higher than the MFTP itself, but the gray line is the truth. Of course, in this setting, the methods are more conservative, but still the FTP method is actually doing pretty well in controlling the false discovery rate. And in this setting, in this particular setting, focused BH is really conservative. And maybe if you have a larger proportion of active genes, you would go for this method. But yeah, it is generally very conservative. Of course, these plots and these values that you see, the comparisons highly depend on these values here, and also the size of the effect that you can observe, a proportion of the genes that are active. But this comparison is generally there, and this is a quite natural situation, I would say. Another way to compare these methods is because, so maybe this is not directly volcano plots, but people who don't know much about the volcano plots, once they have calculated the differentially expressed genes, they would just sort their genes based on beta, so the largest one, absolute largest one on the top, and then select a few of them from the top, like 20 or 50 of them. And this is an indirect way of selecting like a volcano plot, but it is actually, and at the end, the same procedure and same double filtering. So this is what we did here. So we had the fixed p-value threshold. So once we had the genes, we would set the threshold for the p-values and then select top 50. So top means here the largest betas. And then for that set, we would estimate the FTP. And of course, we had already the true FTP. So similar to the previous plot, focused pH is quite conservative in this situation. Although when you have this various gene nullness correlation here, it is a bit conservative, but still you are very sure that you won't run into inflated type 1 error rates. And there are more comparisons of the methods in the paper. I'm not going to bore you with the details and just want to give you a real example. So the data set that I have used here, because we never know in the true data that what the value of lambda you are facing with. So we just wanted to see if we don't know such thing, how we would be evaluating our method. So this is a simple genomics analysis where they have samples from two sets of CE and NE. I'm going to call them, some of them are tumor related and some of them non-tumor samples. So there is the TDP actually should be quite large because there is a clear gene signature of tumor versus non-tumor samples. There are 58,000 features, and the sample size for this study is quite large, and that is one of the reasons why we selected this study. There are 39 and 35 samples in the groups respectively. What we did to kind of go around the fact that we don't know the value of lambda and we don't know the truth, the actual truth for this data set, was to create this resampling procedure where we would just select two small samples from each of the groups, let's say 6 or 12 from each group, and then whatever was left would be the validation set. The validation set has, of course, larger sample size. We would test the validation set, and it would result in some truly DE genes. But then these truly DE genes do still have some false discovery rate involved. So what we would do to make sure that we are not carrying over this false discovery to a discovery issue that we don't know what the values are for, we would permute all the genes that are basically null or not differentially expressed based on the validation set. Once we had permuted those genes, we were very sure that these are really, really null genes. And then this data set would be, this ordering of the genes would be fed into the test set. So we will have the same order, but with different subjects, and then do the whole analysis based on the volcano plot procedure. And we repeated the procedure every time. So the results, if the test set would select genes that were null based on the validation set, that is a red flag for the method. And then we calculated the mean FTP or the FDR. So this is the result. So what you see here is the, again, same drill. The first one is the top gene, and then the second one and the third one. And this is the proportion of the false discoveries. And if you were to actually use the FTP method and estimate the FTP, this is the FTP bound, and this is the median FTP estimate, which of course it is conservative more than the truth, but it is controlling the FDR at the required level, which is this dotted line. So it is very clear that you can run into this issue of selecting with volcano plots, and you would have an inflated type 1 error for the top genes, at least for top like 25 or 50 here. This dip that it goes back to the control does totally depend on the data, so you would never know where it will go back to control, and yeah, this can happen anywhere. There's no easy way of estimating that. And then, of course, we did this whole procedure 1,000 times, and the values that I just showed you were the averages. But if we just randomly pick one of these and look at the validation set and test set, it will give us actually an idea of how it was done and also how it went wrong. So this is the validation set result. So any gene with a certain p-value larger than 5% was selected as active. So these red were active genes. And then everything in the bottom here were null genes, and we had permuted those genes, so they were really null genes. And then these whole set was analyzed based on the smaller sample size and the test set. And you see that the test set selects many, but I have marked some of them that you can see that some of them are still okay in the validation set. So they're actually true discoveries and it is selected by Volcano plot, but there are quite a few that were actually among the null genes. And there's a good chance that they have larger variance, which is the case if you can look at the details of the paper, that generally those that are selected by the Volcano plot and are false discovery are those with the larger variances. And of course, the procedure is based on a closed testing procedure, and it has its own limitations for public use. So what we decided to do to come up with a Shiny app where you can just feed your differentially expressed genes and get the same FTP values for the Volcano plots. Here, I'm just going to focus on the FTP because then the flexibility of the Shiny app is okay with FTP method, but not so okay with the focus pH method because you have to pre-specify your set. So we haven't included in the Shiny app. So this is very simply how it looks. You have to input your data here and select your thresholds, and you will get something very similar to the Volcano plot, but actually the selection is based on these filters here. And then you would get some estimates to look at it closely. So it's a very simple text format that you have to put in, and you can either select among the top genes. So top, again, meaning larger betas, or based on a threshold. And once you have made your selections, you have the threshold for the p-value and you have the threshold for the fold change. Fold change is the same as beta hat or estimated effect size in genomics. And then this is the resulting plot, which would give you the number and proportion of the true discovery. So these two values here are median FTP for this one and TDP for this one. And they also come with a bound, which it can give you an indication of what is the largest false discovery proportion for this bound. And then for this selection, you would see something similar to a Volcano plot, which is easier to grasp, basically. So out of these red dots here, this is the proportion of, so 79% of them are actually a false discovery. So I wouldn't recommend using this threshold, but because of the flexibility of the whole method, you can move around these bars and see how your false discovery or true discovery is changing, and then decide which genes you actually want to choose, and then report the false discovery proportion that is closer to the truth with that. And that concludes my talk. This is my best practice in creating a real volcano with R. Once it is better, I will update you. It doesn't look much like one. And if you want to use the active Volcano plot app, the Shiny app, it is available on GitHub. I have included the link here. If you want to know more details, there is the paper. And of course, if you have any other questions later on, you can always email me. I would be happy to answer your questions. And yeah, that's all.
Thanks a lot, Mitra, for the talk. So very quickly, we have questions from the audience. So the first one is from Thomas Burger. The thresholding on the Volcano plot is also made the other way around. First fold change, then the p-values. Does the problem you point also show up in this setting? Yeah, of course, it actually gets worse, because you are first selecting those with the largest beta, and then among those you are looking for the p-value. The only situation that this won't
be a problem is that you actually know the true beta and use that to sort them, which you never know, or just sort them based on the p-value, which does include the variances into the sorting process, which would be fine.
Okay, thanks. And then an anonymous question: does the use of log-fold change shrunken log-fold changes reduce the inflation of type 1 error in top features?
No, actually, the plots that I showed you are almost all of them are based on the one with VOOM analysis, which is the shrunken method, and it actually makes the problem worse because, yeah, if you look at the issue of shrinking, so you are basically, for those that have a larger beta, you are just pushing the variance to be smaller, then you are actually making the p-value to be smaller on the other hand, and then you are just more likely to select them, and they can still be the false positive. So it is actually the worst.
I think maybe the question was about, because I'm not sure, but I think this log-fold change shrinking is actually shrinking not the variance but the effect size.
Ah, okay, then I don't know about that one. So I have to see how they are shrinking it based on what. So I can't be sure right now to answer that.
Yeah. And finally, Mahendra is asking whether the Shiny app, which I advertised for in the beginning, which is a good idea, is it related to your Shiny app?
So there are two different apps. They are related, but I think the one that Pierre suggested has a little bit more features to select and play around with. Mine is a little bit simpler, but I think the background is also, the method is a little bit different, but not really that different. So you're free to use each of them that you want. They're both valid.
Yeah, so of course I could be right. Okay, and so I guess my answer would be you can attend Nicolas' talk on Wednesday, on Friday, and he will give you a.
Actually, I agree with this one. This is a better answer.
But yes, they're highly related in terms of methodology. But in short, if the Nicolas one can be more powerful if your data allows for permutation testing, so you can incorporate, you can basically estimate the dependence between genes, and it can give you more powerful bounds. But it's really the same idea. Okay. So let's close this. This part of the session, and we have a 15-minute break in theory, but we are 5 minutes behind schedule. But I think it's okay if we. Stephen will say if it's not the case, but I suggest we still take a 15-minute break. And is it okay, or should we keep the original schedule?
No, I think we can have a break. 15 minutes. Yeah, we still have to talk.
Yeah, we did have 5 minutes in the end, so I think it's gonna work.
Yeah.
Okay, so let's. So we are back at 5 p.m.
So Pierre, thank you very much for the whole process and the invitation, but I have another meeting at 5, so I have to drop here, unfortunately. I was looking forward to the talk, but unfortunately I have to